Okay, so good afternoon or good morning. As Andreas said, it's 8 o'clock in the morning here in Chile. So I'm Heidi Korhonen and I'm operations staff astronomer at the European Southern Observatory. So I work on the observatory on Cerro Paranal, which hosts the very large telescope, which you see in this picture, nicely background with the moon. So I'm going, as Andreas said, I'm going to talk to you about how do we actually get spectra from the starlight that comes to Earth. And I mean, I have also put my email address here on the slide. So if you have some further questions after the talk, just feel free to write an email to me. But let's now go to the talk. So if you are interested in abundances, how do what are the stars made of? And you are studying, typically making this kind of plots that you see here. So you are comparing abundance of some element to the abundance of hydrogen. And you have only one dot in this plot. Typically you have many dots if you have seen these plots. And there's actually a lot of work that goes into even this one dot. So the input you need for this one dot alone is the spectra, the atomic data, spectrum synthesis, and stellar atmospheres. So in this talk, I'm going to concentrate on the spectra, and then Andreas Korn after me is going to talk about other points here. So the outline of this talk is I will briefly introduce you to spectroscopy and spectrographs, talk a bit about spectral resolution and the effects of Earth's atmosphere on the spectra. So of course, the starlight happily comes to Earth and then it has to go through our atmosphere, and some things happen there that are sometimes interesting. And then I'm going to finish by talking about how and from where you can actually obtain these spectra. So what is actually spectroscopy? If you look at the Encyclopedia Britannica, it writes, spectroscopy, study of the absorption and emission of light and other radiation by matter as related to the dependence of these processes on the wavelength of radiation. So what you're doing is you are taking the photons coming from a source, I mean, star, whatever, and you are putting those photons in smaller and smaller wavelength bins and seeing how many photons you have in each bin. And then you can see that there are some areas where you have less and some where you have more. So here is a spectrum where you see some features. And here they are identified with the elements and also the wavelength. You can see that here you, for example, have the H alpha line, so the Palma hydrogen, the first transition is at 6,562 angstroms. And in this talk, I've tried to use nanometers because as the wavelength unit, because that is, of course, the normal unit that is used. But astronomers like weird units, and we usually, when we are dealing with visible light spectra, we use angstroms. And 1 nanometer is 10 angstroms. So you just divide these by 10 and you get nanometers. But I mean, most of the talk is with nanometers, but there are some slides with angstroms. So sorry for the confusion. So if you think of spectroscopy, so you want to divide the light into small wavelength bins and study it. So this is, of course, the most, important method for learning about physics and about the astronomical sources. I mean, the simplest way would be for getting this spectral information would be for using filters. Like when we take images with our telescopes, we have filters that select certain wavelengths for our observations. And if you would combine many of these filters, you could study the behavior with wavelengths. But of course, here the size of the resolution element, so how small details in spectral features you would see, would be the width of the filter. So here you see some transmission curves of filters. And you can see that they are typically 100 to few hundred nanometers, the ones that are given here. These are so-called broadband filters that actually take quite a big chunk of the light that comes to the telescope. So if you would combine a few of these, you would have some spectral information, some information on how the source behaves, with different wavelengths. But of course, you wouldn't see fine details with this resolution. Of course, there are also narrowband filters that have a much smaller width of the filter, and then you would have more information. But typically when we talk about spectra, it means that we have actually sent the light through a dispersive element. And what is a dispersive element? So that is the core of the core optical element of an astronomical spectrograph. And with the dispersive element, the angle at which the light leaves is wavelength dependent. So if you control the angle at which the light hits this dispersive element, you will also know where different wavelengths in the end will end up. And there are two kinds of dispersive elements. There are prisms, like Newton used in his famous experiment. And then there are gratings. There's also actually a third kind that is called a prism, which is a combination of a grating and a prism. But in general, these are the two main elements. And in astronomy, we typically use gratings because you get higher resolution with the size of the element, the grating. And the large prisms that would give you a higher resolution are difficult to manufacture. So for gratings, as I said, when the light hits the grating, how it leaves the grating depends on the wavelength. And you have different orders. So if you have just the reflection, that's the 0th order, which is the white light. And on both sides of the white light, you then have the spectrum. So the 1st order spectrum, and it will repeat and repeat. And so you have different orders. So this is the main principle. If you look at the spectrograph in general, what is a spectrograph? What does it look like? This is a very idealized spectrograph. So you have the light. I don't think you will see my cursor, so I don't even try. But on the left side, you have the light coming from the telescope. It will enter the slit. So you only take a small part of the light. I will talk about that later. Then you send it to a collimator. Collimator makes the light rays parallel. As I said, if you control the angle at which the light comes to the grating or the whatever, or prism, the dispersive element you are using, then you know where the different wavelengths will end up. So you have to know the angle at which the light goes to your grating. So then that means that you make the light beam parallel so that you know what is the angle at which the light comes to your grating. Then the grating disperses the light into the spectrum, into the colors, and then it's re-imaged into your detector. CCDs for optical or infrared detectors, if you are working in infrared. So basically what you need for a spectrograph is, of course, your telescope that collects the light, your entrance slit, the collimator, grating, and a camera. And why do you use a slit? So in principle, this is now an image of the sky with some stars. And then you have this black thing in the middle, which is slit. So in this image, which is taken with the acquisition camera, so you see what you are actually getting from your telescope. but the light from the black area is sent to the spectrograph. So that's the slit. So that's why you don't see it in this image. So your object is behind the slit. So if you didn't have a slit, you can do slitless spectroscopy, but then you would get a spectrum from all these objects that you see here. And these objects would then make their own spectra, and they might be overlapping. I mean, if you, especially even here, you can see if you now start making spectra, which would then be horizontally here. If you have an object in at the same height in this image, it would make spectra that overlap. And that would be really messy. So if you really want to get light only from your object, you use a slit to select that part. And also that limits how much photons you get from the sky into your observation. You can also have multiple slits. So here is an image of a field where you have lots of stars, some cluster. And then you have these red squares around them. And this means that from these objects, these are pre-selected objects from which you take the spectrum. So either you make masks where you have many slits, so you can take a plate and cut small slits into it. Or you can, for example, have fibers that can be then put into the locations where you want the spectrum from. And if you use slits, then again, the different slits can't be in the same, at the same height, this image. So the spectra shouldn't overlap. And then you get many spectra, as you see on the right side of this image. So this is how you, the principle of how you take spectra. Then if we talk about abundances and how fine details you want to see, because of course, if you want to get the abundance of an object, you have to get a very detailed shape of the spectral line, the depth, and then get all the light. Get all the details of the spectral line and its depth. Then you need high resolution. So how do you get this? What high resolution? What does it actually mean? So we talk about resolving power, which tells how small details you can actually resolve in the spectrum. It's defined by lambda over delta lambda. So delta lambda is the small step you can see. So R tells you how small details you can see. So if you have R 1000, okay, and now here I can see that I have again angstroms, so 6,500 angstroms. If you have 1000, then your delta lambda, or the resolution at which you would see the spectrum, is 6.5 angstroms. And then, of course, correspondingly, if you go to the R 100,000, that gives you 0.065 angstroms. So you start to see really smaller and smaller details. And this is also goes with the velocity. So, if you interested in, how, you have some processes that produce shifts in the material moving, and then you see the shifts, and then you are looking at the velocity. And at the given resolution, the velocity does actually not change with wavelength, because it depends on the speed of light and the small, so it stays the same. It's the wavelength pins that change, but the wavelength, the velocity resolution doesn't change. And why would you actually, there are a few things about this. Of course, if you want to see small details, you need high resolution, and you could ask, why wouldn't you always want to have high resolution? Some processes like supernova explosions have velocities that are thousands of kilometers per second. And studying that with very fine detail might not be so meaningful. You might still learn something very exciting. Sometimes that happens, but in principle, it's not needed. It depends on your source. But also, I'm sorry. When you are having high resolution, you are taking the light coming from the object and putting it to finer and finer, smaller and smaller bins, which means that you get less photons per bin, which means that you either need very bright targets or large telescopes. So of course, if you have a faint source, it's difficult to do it in very high resolution because you don't get enough photons. But I'm a high resolution spectroscopist myself, so I always like to do high resolution. And there's also one interesting thing that, of course, depending on the resolution, the lines also get diluted because you are taking sort of features and averaging out more and more features, so your lines get blended, and also the continuum, the sort of the level without the lines, you get information from that together with the line if your resolution is not high enough. So here you see these are just actually calculated spectra, synthetic spectra. And with the dashed line, you have the original spectrum, and then you have two solid lines that give you different instrumental profiles. So we call it an instrumental profile. What is the sort of the resolution of the spectrograph? And if you have an 0.1 angstrom instrumental profile, you can see that you don't actually go to the full depth, but you get close to it. You are not getting that much blending of the different spectral lines. Whereas if you go to instrumental profile of 1 angstrom, you get a lot of the lines blend together. You don't see the information, of the individual lines. And also you get a lot of information from the continuum, without lines. So even if you are, it's good to have at least intermediate resolution, simply also to get more information on the features. And I will talk about it a bit more later, but there are some lines that come from the night sky. And even if you are looking at extragalactic objects and are faint sources, you would like to have intermediate resolution to be able to also accurately remove those night sky lines, because they get also blended in your spectrum. But if you go to the really high resolution, then you can really see fine details. So here's some examples of spectra from stars, centered at 6,245 angstroms and giving a 23 angstrom piece there. So you can see many lines and many details. And this is, of course, what you would like to do if you are studying like the abundance is the composition of stellar atmospheres. So how do we usually do the high resolution? We use so-called Échelle gratings. They have two advantages. First of all, you can, if you think of the first examples I showed, so you have your object and you have your slit, and you have your spectrum. So you have only one spectrum, whereas your detector is much larger. So you are having a lot of empty space in your observations. With Échelle grating, you can actually get two-dimensional format. So that permits a broad spectral coverage. So Échelle gratings, they are gratings that have large groove spacing. And they are used in high order, which means that when I talked about the orders, so you have the 0th order, which is the white light, so it has the reflection, and then you have to start to have the different orders. And then when you get to the high orders, they start to overlap. So actually, if you just use an Échelle grating, you would have all your spectra more or less overlapping. So that's why you use another grating, lower resolution grating, as a cross disperser, and you split the orders again. So you separate the orders. So actually what you get is then many spectra from the same object on your detector. Like this. I mean, this is of course an image that has been made look very nice, but when it comes to your detector and the telescope, it doesn't exactly look like this, but I mean, no colors. But actually you see the different orders, you see the different lines. And like here, you see some very strong lines, like in the red, you see this dark area quite high up in the red. There's one very broad dark area. That's, I would say that's the H alpha, the hydrogen Palma alpha sequence. And in the middle, in the yellow, you have two lines. That's, I would say that's the sodium doublet, and so on. And if you then take these different orders and combine them into unstacked spectrum, this is what you see. So this is a solar spectrum taken with high resolution. And you can really see lots of features. I mean, some of them, I mean, like in the blue part, so up when you go to 300 nanometers, 300 to 400 nanometers, you see, it looks like there's a lot of things going on, but those are all spectral lines. So you can, the advantage of Échelle spectrographs is that you can really fill your detector with spectra. So you are using the whole area of the detector, and you can get high resolution spectra of your object over a wide wavelength range. So I will next show you one spectrograph. So this is the telescope where it is. So this is one of the unit telescopes of the very large telescope on Cerro Paranal, so where I work. So you see a guy standing there below the telescope. And it's, the main mirror is 8.2 meters in diameter. So it's not a small telescope. And we have 4 of these, they are identical. So if you would be dropped into one of these domes, you actually wouldn't know at which one you are if you didn't look which instruments are attached to it. Or the 4th one has some lasers for getting artificial laser guide stars. So that one you would know, but the others look exactly identical. So when you collect the light, I mean the light, and then now the enclosure is open, so the telescope sees the sky and it's not sticking out of the dome. In all the cartoons, you always see the telescope sticking out of the dome. I don't know why they don't stick out of the dome. The dome is there to be closed and protect the telescope from the environment, so they don't stick out. So when you start observing, you open the dome, and the dome follows. I mean, when you move the telescope, the dome follows it. So the light comes first to the main mirror, so that 8.2 meter mirror. Then it's directed to the secondary mirror, which is up in the top ring. So I can't now point, but you see this small mirror at the top of the telescope. That small mirror is a 1 meter mirror, so it's not that small. And then it's directed with this secondary mirror back to the center of the main mirror. So there's a hole in the center of the main mirror. And the light can go through it to the instrument that is below the telescope in so-called Cassegrain focus. Or there's actually a mirror in the middle of the main mirror. And this flat mirror can be rotated, and it can direct the light also to the side, so-called Nasmyth foci. So on both sides of the telescope, there is a platform where you can also have instruments. So all these telescopes at the Very Large Telescope and all the unit telescopes, they have 3 instruments, 1 below the telescope and 2 on the sides. And actually during the night, we can choose which instrument we are using. So on this telescope, there's the UVES. You can, which is in this kind of a box. You can also see the box on the left side of the telescope there. So the instrument is attached to next to the telescope, so it doesn't move with the telescope. It moves with the rotating platform, but it doesn't move up and down. And that's important because especially in high resolution spectrographs, even a small change in the position and how the gravity affects the optics, that will actually affect how you see your wavelengths in the spectrum. And now I will very briefly show you the optical elements or the layout of the UVES. I'm not going to discuss this in detail, but I showed you the idealized spectrograph and what is involved in it. This is now a real spectrograph. So you again have the telescope on the left side. Then you have calibration unit and the rotator, because in this kind of a telescope, which is altitude azimuth telescope, the telescope only moves up and down and rotates. So it doesn't rotate with the sky. So the sky rotates on your detector. So you have a derotator that takes away the rotation of the sky. Then you have different optical elements you can put in, like different filters and atmospheric dispersion corrector. And here dichroics for mode selection. So in the UVES, you have 2 cameras, the blue camera at the up and the red camera in the lower right corner. So you can choose to put the light to both of them simultaneously or only to one. And then when the light goes, for example, the red camera, it will go to the collimator and then cross disperser, and you can choose the cross dispersers. And then it will, it will first go to the grating and then it will go to the cross disperser, and from the cross disperser to the camera. You can, depending on the design, you can actually do the cross dispersion before or after. But,
Heidi, you could try to use your cursor. I saw it previously. You could try just using it. I think.
Okay, well, it's just it moves a bit slowly, but yeah, okay, here.
I can see it, and that probably means I can see it. The other thing is that you have about a quarter of time left.
Yes, I'm aware of that. Yes. So thank you. I'm going to the next, sorry. So the take-home messages about this part. You have to choose your instrument wisely. As I said, for a single object, you can get high spectral resolution up to 250,000. But if you more objects at the same time, you are running out of detector area. So you have to sacrifice resolution or wavelength coverage. And because you are dividing the photons into small bins, you are limited to bright targets or need large telescopes. So then some effects you see in the spectra. So first of all, as I said, the light has to go through the atmosphere. So what happens and what appears at the top of the atmosphere is not what we see here at the sea level or on the ground or even on the mountain. Some of the light gets absorbed by the atmosphere, especially by oxygen and water lines. So there are lots of areas where you don't actually have that much signal because the atmosphere takes it away. And basically from 300 nanometers bluewards, you see nothing. I mean, all is taken out by the atmosphere. So there are absorption lines that you see. So here are examples of strong oxygen absorption bands in the spectra in some areas. Of course, these are very well known and they don't change. The oxygen content of the atmosphere hopefully doesn't change. And then there are also water lines. So there's lots of small water lines, blue wards of like 500 nanometers. And here there are several spectra taken at different nights. And I point to some features that sometimes are there and sometimes are not there. And that comes from water. Fortunately, it was actually the absorption lines can be modeled quite well. I mean, oxygen especially, because we know well how much oxygen there is. The water, of course, depends on the night, how much water vapor there is in the atmosphere. But there are tools to remove this. And one of my favorites is the ESO's MolecFit for doing this. There are also night sky emission, which is much more complicated. It gets, sunlight, especially excites OH and makes it glow in the night sky. So there are lots of lines, and these are especially a problem when you are doing lower resolution work, but you see some of these lines also in the high resolution spectra. And there's also light pollution. So depending on how good your sight is. So there are two spectra here. So from a dark side, you basically just get the blue line, which is the night sky lines. And if you have a light site with the light pollution, so human-made artificial light, you see all kinds of lines, especially sodium. And I have had these in my observations. Sometimes you have just huge sodium emission and it's not coming from your source, it's coming from your, lights around. So that's why the best observatory sites have strict policies on lights and light pollution during the night. There are also some other effects you can see in your spectra. So this is one of my favorite papers, and it's an old one. But there were some reports of potassium flares in stars. So you would have suddenly potassium emission in your spectra. But this, in the end, turned out that the observer had been smoking while observing. I mean, this was in the good old days when you actually were really there using photographic plates and doing the observations. Now we just use computers and detectors. But so if you were striking the match in the current location, you actually saw this flash in your spectra and you thought you were recording potassium flares. There are also reports of like seeing lightning in your spectra. So like thunderstorm over the Andes here. You can sometimes see lines from those in your spectra. So be careful if you see some weird lines in your spectra. Make sure that you know where they are coming from. There's also the atmospheric dispersion that can cause slit losses. So the bluer wavelengths are strongly refracted. So if you are orienting your slit wrongly, some of the light actually can go out of the slit. So you should use the so-called parallactic angle, so perpendicular to the horizon. So your slit is oriented so that all the light goes into the slit, even with the atmospheric dispersion. And then reducing spectra. This could be its own full lecture, and I'm not going to give it because I don't have time. If you want, I can give it later, but I mean, this is just a small brief recap of what is needed. And I don't have that much time, so I'm not going to go through this in detail, but you need bias frames, you need to get the constant offset that is applied to detectors to remove it. You need a continuum lamp to remove the non-uniform illumination due to optics and also pixel-to-pixel variations in your detector. You need a line lamp, so-called arc frame, for wavelength calibration. And then you could use a standard star spectrum for flux calibration, but that's not often used for high resolution. And usually these continuum and line lamps are inside the instrument in a special calibration unit. So the take-home message is from here, only a fraction of light from the target arriving at Earth reaches your detector. And if you see some strange features in your spectra, do not immediately write a Nature paper. Investigate first where they could come from. And now I will spend the last minutes talking about where and how to actually get these telescopes. How do you find where to find the right telescope and instrument? So you, in principle, you write a proposal for all the telescopes and you get your observing time, you reduce your data, you do your image analysis and you write your paper. And of course, the proposal writing is the first step. So each observatory has their own proposal cycles. And I mean, typically twice a year or once a year, you write a proposal saying, I want to do this with that instrument, please give me time. And then there is a committee that decides who gets time. And you can, for example, apply from ESO where I work, anyone can apply. And there are also EU funded programs for optical astronomy and infrared astronomy. It was earlier called optical, now it's ORP. And then the NSF funded NORLAB. So these anyone can apply from. Then there are of course national institutes and institutional facilities, and usually only people working in those institutes or countries can apply from these. And these are then clickable links that you can use from the slides. So one thing is that, okay, this is a bit old graph going only until 2013, but you can see that there are about 1,000 proposals, 900 to 1,000 proposals arriving to ESO each half a year. We don't have time for giving observations for everyone because the nights are limited. And we are, even though we have 4 8-meter telescopes, but smaller ones, I mean, we don't have enough time for everyone. So there's a large oversubscription rate that depends on the instrument and telescope, but it's several times. So typically only a fraction of proposals gets accepted. So you have to write a good proposal. And there are basically 2 modes of how to get observations. One is service mode, so observatory does the observations for you, or visitor mode when you go to the observatory. In the service mode, you will get the observations that are predefined. You have to plan them beforehand, tell the people what you want, and then they will execute them and when the conditions are right for your observations. So you get observations in perfect conditions done by people like me. So I observe for other people. That's part of my job. And then in visitor, you can change the observations on the fly, but the weather is what it is. So they both of them have pros and cons. And of course, it's nice to travel sometimes to observatories and see how things are done. You can find information on your target from different databases. There's SIMPAD for stars and extragalactic objects have NED. Here is a query for my favorite star that I did my PhD on. If Andreas used 6 stars, I think I basically only used 1. So that was FKCOM. So you get all kinds of information. This is just a snapshot of it, what you get out of SIMPAD. But there are also available then references, I mean, articles that use reference the star, I mean, data, everything. So SIMPAD is a very good place to look for information on targets. And then you have to know when your target is visible. So you have different programs for using it. Basically, all observatories have their own program, I mean, software for calculating visibilities. Even though you work for ESO, I like to use StarOut. because it has many predefined observatories, and you can even put your own. So here, for example, you can choose a date and the observatory and then put your target and its coordinates, and you will get plots like this. So this is again the FK-COM. Now how we see it in La Palma and how we see it in Chile. So FK-COM has declination plus 24. So plus means that it's on the northern hemisphere. La Palma is on the northern hemisphere, Chile is on the southern hemisphere. It also has right ascension of 13 hours, which means that it's best visible during the northern hemisphere spring, so this time of the year. So for April 8th, this is what you see on La Palma. In these plots, you see how high up on the sky it goes. So horizon is down at the 0, and then zenith is at 90. So it goes almost to the zenith, and it's observable quite high all the night. So these dashed lines give the beginning and end of the night. Whereas for Chile, it doesn't get very high up because our telescopes are at -24, and the declination of this is +24. So it never gets very high up. And here in StarAlt, you also get the information, okay, on the moon. Okay, I don't know what happened here. Yeah. Okay. On the moon, so the moon curve gets here, and the April 8th, the moon is almost new moon, so you only see this dashed line and very faintly in the corner. But you see how far the object is from the moon also, which is important. You can't observe behind the moon. Then you have exposure time calculators. So most last observatories have their own. Here is an ESO one for UVES, where I have put FK-COM in, and I think 60-second exposure. You most likely don't see all the details, but if you go to the link of the ESO ETC, you can play around with it, and you will get then plots of how much signal to noise you have with different wavelengths, with the different settings. And this is of course important. You have to know how long you want to expose, to what kind of signal you have to know what kind of signal to noise you need for your science, and then you can use the exposure time calculator to see how long you have to actually observe to really get this signal. So the last take-home messages are, so anyone can apply observing time from certain places. And also what I didn't really say, but plan your observations very well, because telescope time is expensive. 2-meter class telescope costs like 3,000 euros per night. If you go to the 8-meter class telescopes, like where I work, it's 35,000 euros per night, basically €1 per second. And you don't want to waste those seconds and photons. So that was all I wanted to say. In the end, there are some slides on, I have collected information on telescopes and instruments. So when you get these slides, there are clickable links here, then you can have a look at them. So I have collected information on the largest telescopes. I mean, with larger than 8-meter mirrors, and what instrument, I mean, high resolution instruments, and also what kind of access you have for them. So there are 3, I mean, like you see, this is behaving a bit funny now again, but yeah, like here you see the high resolution spectrographs we have on Cerro Paranal in Chile at ESO, and then I have also 2 slides on other telescopes of interest. So some that have at least the 3.5-meter mirrors and universal access. So I'm not going to go through these, but they are for you. So I finish, and I think actually on time, because I think I started a bit late. So
you did. That's correct. Thank you very much, Heidi. Great, wonderful. Thank you very much. Before we come to some questions, there were no questions in the chat, but before we come to some questions, you may have realized a certain feature of Heidi's presentation, and you will recognize this feature again during Andreas' coming up, namely that we have these takeaway messages as green boxes or even as slides with a green background. This is something that we decided we wanted to have as a theme for these observational schools. So you will meet this again in the autumn when we have the second round of an observational snacks. Before we go on to Andreas' talk, are there any questions? There were, as I said, I could find none in the chat, so maybe there are nonetheless some questions. I think Heidi's talk was very clear, and we deliberately asked her to keep it simple in order to for this diverse audience to be able to grasp the the basics of stellar observations. But there may still be some questions.
Yeah, and as I said, if you have some questions that you want to ask later, you are always welcome to write to me. I mean, if you want more details, I mean, as Andreas said, this was kept at the very, I mean, sort of not detailed level.
Very generous of you, Heidi.
Yeah. So I thought
there's things in the chat, but it's not.
Okay.
Chris,
okay.
have a question in the chat, or did
Chris asking?
Chris was raising his hand, yes.
Oh, sorry, I can't. Yeah, now I see it. Sorry. Yeah, Chris, please go ahead.
Yeah, please, just to reemphasize things that she said. The resolution numbers look frighteningly large. They, whenever you're dispersing the spectrum more and more, of course, you're getting fewer photons per pixel. The good news here, though, is that many, many good abundance studies can be done at a resolution of an R of, say, 50,000 or 45,000. You don't really need 250,000. And the reason is that ordinary stellar atmospheric line broadening is much larger than that.
Yeah,
exactly. So it depends a lot on what you are actually studying. Like me, myself, I don't do abundances. I actually study, I mean, stellar, I mean, surface inhomogeneities. So I actually want to see how the spectral line profiles change. So I need very high resolution because I'm not only looking at depth of the line like you would do, or how much, I mean, the abundances, but I want to see small wiggles in the line profiles
Right.
too.
Right, exactly.
Yeah, so I think Andreas will go more into this, but of course, if you have, there's a science case for every resolving power. If you want to study isotopic shifts, you will want to go for the highest resolving power you can get. But in general, the argument is very true that there is already some velocity shifts, macro turbulence as we call it, and or rotation in normal late type stars that make the window 40 to 80,000 a very good one for us. Other comments, other questions? Please don't be shy. Raise your hand or just speak up, both is fine. Everybody's very, very quiet today, but it's good. I mean, you're here to take in information, and that's perfectly fine. If there are no questions, we have more opportunities. We have the breakout rooms, and then we have the roundtable discussion at the end. So if a question matures in your head, you can ventilate it in the room, and then maybe a good scientific question arises from it.
You got a question from Aurora, Andreas.
Oh, sorry. I don't see that. Yeah. Oh, please, Aurora, go ahead.
Andreas, you can read it, please. It's
sorry,
in the chat. Yeah.
It's in the chat. Sorry. Yeah. So I moved the chat in order to see the participant list, and now it's in the chat. Okay. Here we go. Atomic spectra are quite well known, but is there something unexpected in your observations? Oh, this is a very open question.
Yeah, it's an interesting question. And I mean, yes, we know the atomic spectra quite well, but I mean, of course, I mean, I would say that there's still some work to be done also in that. I mean, we don't know all the species, and especially if you go to, I mean, molecules, then you start to have more problems, and especially if you go to wavelength regimes that we have not used so much, like submillimeter with ALMA. Often when they take a spectrum they have half of the lines, they actually don't know what they are, because I mean, there is no information on this. And also in the, let's say, the atomic lines in the visible range, sometimes, I mean, you have things coming from the interstellar medium, for example, and they are at a different velocity than your star is. So you have some lines that are shifted, and then it's not always completely, I mean, clear where they come from. And there are these diffuse interstellar bands, for example, that are a bit puzzling and things like that. So yes, we know atomic lines quite well, but there are still lots of things that we don't necessarily know. And especially if you take a look at extragalactic objects, I mean, the high redshift, and again, because of the redshift, the lines get shifted. So sometimes it's difficult to identify what is going on.
Yeah, that's right. It's work in progress on all fronts, also on the atomic and molecular data laboratory astrophysics, AOM physics, as it is called. Thanks again, Heidi.
Okay, thank you.
Okay, thank you very much. It was a very interesting talk indeed, Heidi.